Power in conductors. Let's start with Joule's law. Joule's law calculates the power dissipated by some medium that is conductive. And if we look at the integral, we can, from our circuit theory, think of this as a P equals voltage times current. So we have total power being dissipated by a conductor. It's a volume integral of the electric field intensity dot the electric current density. So P equals V times I. So that's the circuit theory equivalent. Let's proceed with that. So the argument of this, anytime we do a volume integral or an integral of something to get a total quantity, the argument of that integral is some kind of density. So we can argue that this E dot J is the power density in a conductor. So P sub D, our power density, is E dot J. Now let's work on this a little bit. We have Ohm's law for electromagnetics. This is like a V equals IR, and it's J equals the conductivity times E. So back to this equation, power density E dot J, we can replace J with a sigma times E. While this sigma is just a constant, we can move it to the outside. So we have a sigma of E dot E, and the E dot E is the magnitude squared of the electric field. So in summary, the total power being dissipated by a conductor is a volume integral of the conductivity times the magnitude of the electric field squared. And we can take away from this, the sigma times the electric field squared is the power density of what's being dissipated by a conductor.